So in the previous lecture, we looked at the Thomlin problem, we defined the Thomlin problem, but we told that the central problem is to determine equilibrium states of a composite, of an isolated composite system containing several subsystems that are separated by a wall. So it is an isolated composite system, that is the overall system is isolated. That means it cannot exchange matter and energy with the surrounding. However, the system is a composite system, that is contains subsystems like alpha and beta, and the subsystems are separated by a wall. The wall initially has these internal constraints such as rigidity, impermeability, and adiabatic. Right? Adiabatic means it does not allow heat transfer. Then, if you remove these internal constraints, you want to see what will be the equilibrium states, how the equilibrium state of alpha and beta will be defined. Now, the equilibrium states will be defined in terms of, you can define in terms of temperature, pressure, you can define also in terms of extensive variables like U, V, N, right? So, now comes the first postulate where we define this entropy function, which is a function of extensive parameters U, V, and N, and we tell that the entropy of each subsystem is a function of the extensive parameters of that subsystem. And we tell entropy is an additive function, right, and is an extensive property, it's additive. And we tell that the values assumed by these extensive parameters U, V, and N in the absence of any internal constraint are those that maximize the entropy over the manifold of constrained equilibrium states. That means the values assumed by U, V, and N, N1, N2, N3 in different subsystems are those values in absence of any internal constant, are those values that will maximize the entropy, right? Now, if you think of the total entropy of the system, right, of the composite system. Now, when I talk about maximizing, we are talking about extremizing a function, right? When we extremize a function, first thing that we do is we check that the function, like for example, here the function is S, so ds has to be equal to 0, right? That is the extremum condition, and that is what we solve for. And then we check whether this extremum condition corresponds to the condition that is extremum, whether it is whether the second derivative, that is d2s, is less than 0 or greater than 0. If it is less than 0, then definitely it is maximum. If it is greater than 0, then it is a minimum, right? So if we tell d2s is less than 0, that means entropy is maximized. And in the when entropy is maximized, the equilibrium state described by these values of these extensive parameters in the subsystems are will give us the equilibrium condition or the equilibrium between phases or equilibrium between the subsystems, right? That is the idea. So so that is the key problem or central problem of phase equilibrium, right? That's the central problem of phase equilibrium. Now, and I also told that, see, if you have these subsystems or we can call these subsystems as phases because these subsystems are chemically homogeneous, right? And physically they can be considered as chemically homogeneous, physically distinct, that is having distinct physical properties like density and so on, and they are also mechanically separable, right? Mechanically separable. So these are your phases, and phase and subsystem. I will show that the phase that we are talking about, and we are talking about multiphase. So in multiphase is nothing but like but subsystems separated by these boundaries or phase boundaries or wall, and this wall basically you can impose constraints on them, and then you can remove the constraints or relax the constraints, and you can find out the equilibrium state. Now, one thing you have to remember that in macroscopic thermodynamics, in macroscopic means the way we are talking about, right? We haven't yet connected it to the microscopic. We have done some molecular interpretation, but we will go further into that. But before we go into connecting the microscopic world of atoms and molecules with the microscopic thermodynamic quantities, we have to tell this that in macroscopic thermodynamics or right, in microscopic thermodynamics, if one can describe the condition or state, right? Condition is a state of a system, right? Using only thermodynamic variables. They can be extensive variables, they can be intensive variables, but if we can describe the state of a system by using only thermodynamic variables, then basically what we are describing, so if one can describe the condition or state of a system using only thermodynamic variables, what you are basically describing is a thermodynamic. So we are, so if one can describe that, so basically that is equivalent to, this is basically the equilibrium state. Now this equilibrium state is in, so one of the equilibrium states, it can be a constrained equilibrium, it can be an unconstrained equilibrium. Unconstrained equilibrium is the one where you have removed all constraints, right? You have removed the constraints that you impose on the walls. If you remove that, but whatever it is, either constrained or unconstrained, if we can describe the state of a system using only thermodynamic variables, then what we describe, one basically describes a thermodynamic, so it is one equilibrium, so it may be a constrained equilibrium, but it's a one thermodynamic equilibrium state of the system. And therefore, when I talk about this axiom of maximization of entropy, what I am talking about is that you have overall, there is an isolation, right? Overall the system is isolated. So giving this, so I can giving these symbols means here like this, when I give this marks here on the boundary. So what does this mean? This hashes mean basically that this means the overall the system is isolated, right? Overall it is isolated from the surroundings, right? But this is the wall, right? Wall, and you remove internal constraints on the wall. So that means you make the wall flexible, you make the wall permeable to the exchange of matter, and also diathermal, that is your exchange of energy. Then you have, say for example, this alpha and beta, so which contains U alpha, which can be described by U alpha, V alpha, and say N I alpha, and here is U beta, V beta, and Ni beta. These values, okay, in absence of these internal constraints, are the values. These values will basically maximize the entropy. So when I tell maximize the entropy, that means for these values, ds of the overall system, overall isolated system, will be equal to 0. Right? That is the first condition. That is the extremum condition. Then you can go to the second condition. That is that d2s will be less than 0, right? So that it means that entropy is maximized. Now comes thus another thing that we told, that it has to be continuous and differentiable and monotonically increasing function of energy, right? It's a continuous function of energy, right? S is a continuous function of energy. It's a monotonically increasing function of energy, that is del S del U has to be greater than 0. Del S del U has to be greater than 0, right? That's so the partial derivative is greater than 0, and it is continuous and differentiable. That means if I know S as a function of U, V, and N, right? If I know S as a function of U, V, and N, I can also define U as a function of S, V, and N. By the way, we have done that. Say, for example, when we have written, so for a single component system, when we have written du equals to PdS minus PdV, that is the combined statement of first and second law, we could express ds as 1 by T du, right? ds is 1 by T du plus P by T by plus P by T dV, right? So both are possible, right? You can write U as a function of S and V and S as a function of U and V, because S itself is a continuous and differential function of internal energy. Not only that, S is a monotonically increasing function of U, right? Del S del U has to be greater than 0. Right, as a function, when V and all the species small number are kept constant, del S del U has to be greater than 0. Another thing, since it's an extensive parameter and it's a function of other extensive parameters U, V, N, now you can think of S as a homogeneous first order function, right? This is called homogeneous first order function. S itself is an extensive variable, that's why it's a homogeneous first order function of extensive parameters. That means S is a function of U, V, N1, N2, Nr, right? Now, if I multiply U by lambda U, means I am just basically using lambda as the multiplication, the parameter. So, I am changing U to lambda U, V to lambda V, N1 to lambda N1. So, lambda can be fraction, lambda can be a whole number. Like if I put lambda equal to 2U, say for example S. So, if I think of an example, S, and instead of U, I am telling it is 2U, 2V, and say 2N1, so it's a binary system, say 2N2 is the same as writing 2S UV N1 and N2. That means if I have changed the mole number by twice, mole number of each species by 2 times, and U has become 2U and V has become 2V, so I have basically extended, means I have basically changed the extent of the system, right? Instead of U I have doubled it to 2U, instead of V I have doubled it to 2V, even the mole numbers of each species have been doubled. Then basically this means the entropy itself has been doubled, right? So that's the idea. So it's a homogeneous first order function. So this is basically what we are trying to say here is this lambda, basically it is, so if I tell homogeneous nth order function, then it is lambda to the power n. Here lambda n equal to, now if I tell homogeneous first order, so if I tell this way, say z, I will say z is a function of x and y, and I am telling that z is a function of a homogeneous nth order function of x and y, then if I just multiply lambda y, this will basically give me a lambda to the power n z. Now it's first order, that means n equal to, right? So z is a homogeneous first order function of x and y. Z is a first order function of x and x, right? So here n equal to 1. Now let us put lambda equal to 1 by n is the, say n is basically the total number of moles, right? So you have n1 moles of species 1, moles of species 1 or component 1, and then L2 moles of what is called this component. So moles of component 1, it's a chemical component 1, and N2 moles of component 2. Similarly, you are telling NR moles of component R. then the total number of moles is N, which is N1 plus N2 plus dot dot plus. Now I have put lambda be 1 by N, which is basically 1 by summation Nk, where summation over k, and k goes from 1 to r, right? Now if that is so, then S, so as I told, see if you look at this definition, S of lambda u and all these things is basically lambda is uv n1 into n. So here it will be S of uv n1 into n1. Here it will be basically, so I have to just put, I can write this as 1 by n S uv n1 n2. Now you see what we are writing it as is lambda is coming here, lambda is coming here. So this is basically 1 by n. So you can write this as S u by n, v by n, n1 by n, and r by n, and then you have also an n here because 1 by n has to be multiplied, right? So n into 1 by n is 1, right? So basically what we are telling is S u v n1 into nr, you can immediately follow that we have this 1 by n, here also 1 by n, here also 1 by n, and here there should be an n because lambda itself is 1 by n, right? Lambda itself is 1 by n. So now if that is the definition, now you can think of this small s uv, say for example if you have a single component system, if you have a single component system, n, capital N is nothing but n1, right? You have only one component. So n1 by n is basically equal to 1 because n1 equal to n, right? You have a single component system. So the small s is basically entropy per mole, right? Because there is a total number of moles, right? Entropy per mole, and is a function of u. Small u is internal energy per mole, small v is volume per mole, right? Volume per mole, which is equal to capital S u small, a function of small u, small v, and mole, right? So basically what we are telling is that since this expression is true, right? Because n by n is 1 and u by n, v by n, so for a single component system, the molar entropy is a function of molar internal energy and molar volume, and this is not and this is just going to be as a function of molar energy and molar volume, right? That is the idea. So u by n is energy per mole. So S, so what we are telling is S by n is entropy per mole, and we are writing it as small s, and small s is called small s. Let me use small s as this, and small s is capital S by capital N. Capital S is your extensive parameter, small s is not an extensive parameter, it's per mole, right? And small s is a function of small u and small v, where small u indicates internal energy per mole and small v indicates volume per mole. And we could have written x1, x2, so if it is a multi-component system, it would have been uv, and here it would have been x1, x2, these are the mole fractions, right? xr, where x1 equals to n1 by n, and xr equals to nr by, right? And the very important thing that comes in, that is the third law basically states what? That entropy vanishes, right? For a perfectly crystalline substances at absolute zero, entropy vanishes. What we are telling here is entropy of a system vanishes in the state for which del u del s v n1 n2 equal to 0. Now, what is del u del s? Now, if you look at that, we have already shown that. So when we wrote du equals to del u del s and v ds, plus del u del v s v, and this we wrote as TdS minus PdV, and as you can see, del u del s v is nothing but, and what we are telling, that entropy system vanishes in the state for which del u del s v is 0, right? Now only thing is, I have added another potential that is called the chemical potential, right? So P is your mechanical potential, T is your thermal potential, and so we have added another mu dN, where mu is your chemical potential, and now it becomes V n, and here it becomes S comma n, right? So here it is S n. Now this is T, so we are telling that S vanishes or S becomes 0 when del u del s or T is equal to 0. If del u del s Vn, which is equal to T, is equal to 0, then S equal to 0 for perfectly crystalline substances, right? That's it. Now you have defined, so basically as S is a continuous and differentiable and monotonically increasing function of U, you can write U also, because of continuity and differentiability with respect to the energy, you can write U as a function of S V n, right? And if you can do that, then we have shown, and this is exactly what I am writing, because it's an exact differential, whether it is S, whether it is U, because they depend only on the state of the system, they depend on the initial and final states, they do not really depend on the path, therefore these are all exact differentials. So if it is an exact differential, you can write du, for a simple system you can write du, because del u del s keeping v n1 n r fixed ds, and del u del v keeping dv fixed, and then summation I equal to 1 to r, del u del ni or del u del nj, j equal to 1 to r, is v n1 nk, which is not equal to j. Remember, so when I write nj here, when I am writing j here, then what we are fixing? We cannot fix j, right? Because we are changing internal energy with respect, we are seeing the change in internal energy with respect to nj. So what we are fixing is SV, N1, and all the other species concentration, or all other species mole numbers. Say for example N1, N2, N3, Nk not equal to j up to n, and there is a T and j, right? So once we have done that, now you see del u del s, exactly what we told is T, del u del s is T, and minus del u del v is P, right? That's what we have defined. And so pressure is the mechanical potential, temperature is the thermal potential, and chemical potential is del u del nj, where S, V, and N1 and up to Nk, K not equal to J, these are all fixed, right? And you get mu J, that is the chemical potential of the J for, right? So that's the, so now you have this equation, and that is the same statement of combined first law, second law, which is, but it includes now components or chemical species, right? So you have du is TdS minus PdV plus mu1 dN1 plus mu2 dN2, similarly plus mu r dN1, right? Now we also know that, so again I am repeating, delta W is minus PdV and delta Q is TdS. This quantitative heat flux of the system, which increases the entropy of the system, and then quantitative chemical work. Then if we define the same way, it will be mu dN, right? Delta WC is J equal to 1 to R, mu J dNj, right? So you have the heat, the thermal work or heat input, and then you have the mechanical work, and then you have a chemical work, right? Now if you see, these are called equations of state, right? You also require that, right? You require T as a function of ASV N1, P as a function of ASV N1, right? These ASV N1 to NR, these are all extensive variables, but T itself is not. P itself is not, mu itself is not. So if that is so, these are called homogeneous zeroth order functions. homogeneous zeroth order function. So basically, if I multiply s by lambda, v by lambda, so basically there is a multiplication factor. Again, I am trying to change, by multiplying with lambda, what we are doing is, we are changing the extent, right? We are changing the extensive variable, right? Extensive variable, definitely it will change, right? If I make s to lambda s, v to lambda v, n1 to lambda n1, so what we are changing is the extent of the system. But remember, T does not care about the extensive system because it's an intensive property or a point function, right? It's a point function of all these extensive parameters. As a result, so this is a homogeneous zeroth order. So this is basically, what we are trying to say is z. If z, let's not call it z, let's call w as an intensive parameter, or v as an intensive parameter. No, not v. Okay, let us call small z parameter, the function of x and y, is a function of x and y. Now I write x is changed to lambda x, and this is y. That's homogeneous zeroth order, which is lambda to the power 0 z x y, which is z. Right? So it does not. So z, which is an intensive, here the small z, which is an intensive variable, does not depend on the how much I have changed the extent of x and how much I have changed the extent of y, which x and y, that x and y are the extensive parameters, right? But z does not change, right? So this is something that is very important, and this is something that we have explained when we define intensive parameters, right? Intensive parameters are point functions, they can define the point, right? So basically this is, it's always some sort of a ratio, right? Del u del s, for example. So these are called potentials, and these potentials are defined at a point, right? You define them at a point, and as a result they are homogeneous zeroth order functions of the extensive parameters. Now you can write it in the entropic form, right? As I told you, that you can write it in terms of s as a function of uvn or u as a function of svn. So here, for example, I am writing in the entropic form. So ds is del s by del u vn. Del s by del u is nothing but 1 by t, right? It becomes 1 by t. It is identified with 1 by t. Now you have del s del v, which is basically minus p by t. Del s del u del v, and del u del v is del u by del v is minus p, and del s by del u is 1 by minus is 1 by t. So this becomes minus p by t. This is 1 by t minus p by t, and this is mu by t. Del s del n is nothing but del s del u del n, right? You are using chain rule, so you can write this way, del s del n, which is mu by t, right? So you can express the exact differential ds in terms of del s del u, del s del v, and del s del nj are the intensive coefficients, right? One is 1 by t, then there is minus p by t, and then mu by t, right? So you have. Now let us consider, what does thermal equilibrium mean? Now, if I have to consider what does thermal equilibrium mean, we are basically considering two simple systems. Simple system means you are only thinking of internal energy, volume, and mole number of species, right? Of different species. Now you have these two simple. There are two simple subsystems, right? These are two simple subsystems. We are thinking of two simple subsystems, and the one, okay, and I have defined this as 1 system 1 and then system 2, and this is 1, 2, and we have, say, a single component in 1. You can do it for multi components also, in 1 and in 2. You can do it for, like, you can do it for nj. J equals 1 to R. So you have like the R species or R components. And see, and what we are telling is that we are making this wall that we have here, this wall is rigid. That means it does not adjust with respect to volume changes, right? It does not respond to volume change, right? It does not move, it cannot move. It is rigid. And then I am telling it also is impermeable. That means it does not allow species. It does not allow species to move. So it is rigid and impermeable. But it is diathermal. That means it allows the flow of heat. Now, see, if heat is moving around, right? You do not allow the flow of matter. That means from subsystem 1 to subsystem 2 or from subsystem 2 to subsystem 1, no species can flow, right? There is no way species can flow because the wall is impermeable to the exchange of species, right? Exchange of components, right? So no, there is no flow of species that is happening, right? No mixing of species that is happening. No adjustment of volume that is happening. Only thing is diathermal. That means it allows the flow of heat. As a result, internal energy, right, which is sensitive to the flow of heat, is going to change, right? U1 and U2, right? These two terms are free to change. U1 and U2 are free to change. However, the total energy, which is U1 plus U2, is constant, right? So what we want to see that the values of U1 and U2 are such as to maximize the total entropy, right? Total entropy. And what is total entropy? Total entropy is the sum of subsystem entropies, right? Which is S1, it's a function of U1, V1, and all this N1, N2, N3 up to Nr. Similarly, S2, U2, V2, S2 again a function of the external parameters of the subsystem, right? U2, V2, and all this N2, right? To Nr, right? So now what we are telling is total entropy is S1 plus S2, right? Which is the function of U. S1 is a function of U1, V1, and all, and S2 is a function of this. Now, entropy change. If you think of the entropy change, which is basically we now write the. So we can write this as ds. ds is nothing but del S1 del U1 du1 plus del S2 del U2 du2. However, you note that U1 plus U2 is equal to constant. So du1 plus du2 have to be equal to 0. Right? So now you are using du2 equal to minus du, right? So from this you can write du2 is equal to minus du. Right? Now you have ds, which is del S del U. Del S del U is 1 by t. So del S del U for subsystem 1, which is basically 1 by t for subsystem 1, du1 plus 1 by t2 for and du2 is for subsystem 2. But du2 is equals to minus du1, right? So I am substituting here. So here I basically write, instead of du2 I write minus, and instead of du2 I put du, right? That's what we are doing, right? We are substituting du2 by minus du1. So if you do that, then what happens is you get ds, which is equal to ds, which is equal to 1 by t1 minus 1 by t2 and common, and du1 is common. Now ds equal to 0 means 1 by t1 should be equals to 1 by t2, right? So 1 by t1 means temperature in subsystem 1 equals to 1 by temperature in subsystem 2, or we can write consistently that T1 equals to T2, right? So we can immediately write that T1 equals to T2. So this gives you the condition of thermal equilibrium, right? And this thermal equilibrium is achieved when there is flow of heat that is allowed. Say for example, if flow of heat is not allowed, then there is no T1 equal to T2, because the temperatures cannot change, because the internal energies cannot change, right? So as soon as we may allow the wall, the heat transfer to occur through the wall, then immediately there is this thermal equilibrium that got established, and that thermal equilibrium basically is a result of extremization of entropy, right? And we will later show that T2s indeed is going to be negative in this case, right? So basically this gives you the thermal equilibrium condition. So this is your thermal equilibrium. Remember, we are taking two subsystems. If you do take n subsystems, the same idea will occur. So it will be like if I take subsystem 1, subsystem 2, subsystem 3 and subsystem 4, and in all cases if you have these different walls and all of these walls allow heat exchange, then ultimately the equilibrium that we will get, thermal equilibrium that we will get is T1, T in subsystem 1 is equal to T in subsystem 2 is equal to T in subsystem 3 and T in subsystem 4, right? But if you put constraint of adiabatic, then you will have a temperature gradient, and really you will establish a fixed temperature gradient, and this temperature gradient cannot change, right? It's a constrained equilibrium, right? But in unconstrained equilibrium, you have all the temperatures to be equal across all subsystems, right? Now this also gives you a way of looking at driving force. Assume that, say for example, I have a subsystem, again I have this system, composite system. Let me draw it properly. I have this composite system, and in that I have this wall, and I have T1, and I have T2, right? And I am telling that T in 1 is greater than T in 2, right? That's what we have assumed. Now delta S is 1 by T1 minus 1 by T2 into, right? That's what we have found, right? Ts equals 1 by T1 minus, so 1 by T1 minus 1 by T2 delta U. Now delta S greater than 0, right? The entropy of our system increases, right? It has to increase, right? It cannot decrease during heat flow, right? So it has to increase during heat flow. Then delta S has to be greater than 0, right? Because it increases during heat flow. Now since T1 is greater than T2, delta U1 has to be less than 0. That is, delta U1 is associated with the change in internal energy of system 1, right? So since T1 is greater than T2, right? T1 is greater than T2, right? So as a result, T2 minus T1. So this if I write, so 1 by T1 minus 1 by T2 is equals to T2 minus T1 by T1, right? And remember, this is absolute scale, so temperatures are all positive, right? T1, T2. So the denominator is positive, but here T1 is greater than T2. Therefore, T2 minus T1 is negative. So delta U1 has to be negative. That means delta U1, that means the internal energy of system 1, which has a higher temperature, has to decrease, right? And so if it has to decrease, that means it has to basically release heat, right? And heat has to enter system 2, right? So heat flows from system 1 to system 2 such that the internal energy of system 2 changes to increases, and internal energy of the subsystem 1 decreases, right? So it gives you our natural heat flow direction also, and it also tells you if there is a temperature difference, that heat flow will be such that heat will flow from higher temperature to lower temperature. This is something again from Clausius inequality we have shown, and the same thing is what we are invoking here. And you can see that not only this extremization of entropy gives you the thermal equilibrium, it also gives you the natural direction for heat flow, right? So it is or spontaneous direction for heat flow. Now think of mechanical. So if you now have to consider mechanical equilibrium, then you make the wall not only diathermal, that means not only allow the heat exchange, but also make it flexible or movable, right? We have made it movable. So So what are the constraints? The constraints are total U1 plus U2 has to be constant, and V1 plus V2 have to be constant, right? Although V's can change, right? For a subsystem 1 and subsystem 2, V1 plus V2 have to be constant. So du2 equal to minus du1, right, because u1 plus u2 is constant, and similarly dv2 equals to minus dv. Now again we look at the extremum principle. Now change basically for subsystem 1 is del s1 del u1 du1 del s1 del v1 dv plus del s2 del u2 du2, that is for subsystem 2, and del s2 del v2 dv. Now del s1 del u1 is 1 by t1 and del s2 del u2 is 1 by t2, and you see there is du2 is nothing but minus d1, so you can write 1 by t1 minus 1 by t2. Similarly you can write in this case del s del u, again from chain rule what you get is p by t, so this becomes p1 by t1, and again here dv2 is written as minus dv1, so therefore there is a minus sign and there is p2 by t2. Now you can see here this has to be equal to 0. Now since du1 and dv1 can change arbitrarily, each of these coefficients, right, this one has to be separately 0, this one has to be separately 0, right? So because the change in u and change in v are arbitrary, right? So this has to be separately 0 and this has to be separately 0, so this has to be equal to 0, this has to be equal to 0, so 1 by t1 minus 1 by t2 equal to 0 basically gives you t1 equal to t2. Similarly, now if t1 equal to t2, obviously this equation will give you p1 by t1 equal to p2 by t2, and since t1 is equal to t2, this basically gives me p1 equal to t2. That means the pressures in subsystems 1 and 2 have to be equal, right? When again they were not equal when we did not allow the volume to change. How? By making the wall constrained, that is rigid, right? We did not allow the wall to move. Now we are making the wall to move, and since we are making the wall to move and the total volume is constant, you can immediately see that the equilibrium, mechanical equilibrium basically means that the pressures in subsystem 1 and subsystem 2 have to be equal, right? Apart from temperature, so temperature equilibrium is thermal equilibrium, and this is the equilibrium in pressures. The pressures are the same, so P1 equal to P2, right? If there is a pressure gradient, then there will be a flow in, there will be a change in volume, right? There will be a change in volume if there is a pressure gradient, right? If there is a, so if you create pressure gradient, then there will be a change in volume, right? The wall will start moving, right? And that is what happens even in weather changes and all. And if you create a pressure gradient, it wants to the overall you want to release this pressure, and as a result there is this different in open systems there is this flow work that happens, and due to this flow work you get all these rains and stuff, right? So that's that. Now think of chemical equilibrium. Now think of rigid. Again, you can impose the condition of rigidity. You can impose the condition of rigidity. But you make the wall diathermal and permeable to flow of component 1 and impermeable to flow of all other components. So we are telling, now we are thinking of chemical equilibrium of component 1. So basically I select one membrane which allows component 1 to diffuse or component 1 to transfer between subsystem 1 and subsystem 2, but none other component can. And then we are also talking about diathermal wall. That is the diathermal wall means that we are allowing heat flow, right? Heat flow is allowed and flow of species 1 is allowed. Now if you have that, you have 1 by T alpha du alpha. So you have two subsystems. Again the subsystems are alpha and beta. The subsystems are alpha and beta. Right, and it's overall isolated. Now you have 1 by T alpha du alpha and mu alpha by T alpha dn1 alpha, right? We are only allowing flow of species 1 or exchange of species 1 between subsystems alpha and beta, and 1 by T beta du beta plus 1 by mu 1 beta by T beta dn beta. Again du beta equals to minus du alpha. Why? Because u alpha, since u alpha plus u beta is equals to constant. Similarly, n1 alpha plus n1 beta equal to constant. So dn1 beta equals to minus dn1. So again we can see from this equation, if you just change dn1 alpha, and this is dn1 beta, which is nothing but minus dn1 alpha. So you have again, and du beta is written as minus du alpha. So you basically rearrange this equation and you get this one, and you get 1 by t alpha minus 1 by t beta du alpha, and mu1 alpha by t alpha minus mu1 beta by t beta dn1 alpha, right? Because I have substituted dn1 beta by minus dn1 alpha. So immediately I get these relations, 1 by t alpha equals 1 by t beta, which means t alpha by t beta, and mu1 alpha by t alpha equals to mu1 beta by t beta, which implies mu1 alpha equals to mu1 beta. Now the chemical, as you can see, the equilibrium is such that N1 will change such that the chemical potential of component 1 in alpha subsystem should be chemical potential of component 1 in beta subsystem, right? Or you can think of this as alpha phase and beta phase, and you can see that mu1 alpha should be equals to mu1 beta at equilibrium. Now you can extend it to multi-component system. So next time I will talk about another important relation called Gibbs-Duhem relation. So we can see now that for simple systems, by just extremization of entropy, we can understand the chemical equilibrium, the mechanical equilibrium, and thermal equilibrium. So if you have multiple subsystems, say alpha, beta, gamma, so basically, or alpha, beta, gamma, delta, the equilibrium conditions are like T alpha equals to T beta equals to T gamma equals to T delta. Similarly, mechanical equilibrium indicates P alpha equals to P beta equals to P gamma equals to P delta. And for each species, say for example, if I allow different species it to be permeable to the flow of different species between the subsystems, we can tell, right, for each species, say I have two species, I have mu1 species, the component 1 and component 2, so mu1 alpha equals to mu1 beta equals to mu1 gamma equals to mu1 delta, and mu2 alpha equals to mu2 beta equals to mu2 gamma equals to mu2 delta, and so, right, if you have R species, so you have to solve all of this. These are your thermodynamic equilibrium conditions for a simple system where we consider contributions which are chemical, mechanical, and thermal. We are not considering here magnetic or electrical. So if you want to extend to that magnetic, electrical, or surface contribution stuff, we have to integrate. We have to also incorporate those into our description of equilibrium. But here we are considering this equilibrium. But what we have found out most importantly is that whether we so that with this very simple axiomatic approach, we do not violate any of these laws, right? And once we do not violate these laws and we satisfy the laws, right, the total energy cannot change, the total mole number is fixed, and immediately you can see that what follows are the definitions of thermodynamic equilibrium, right? What are the thermodynamic equilibrium conditions in terms of thermal? So thermal equilibrium, chemical equilibrium, and mechanical equilibrium, right? So we get it back. So in the next lecture, we will start with one of the another important description where we will look at Euler equation stuff. So till then, so let us understand this and absorb this concepts that I have taught, and I think this will help you in understanding the overall idea of equilibrium and how to achieve it. And this will be a very general. This is a very general approach, and you can see that you can extend it to multi-component, multi-phase equilibria. If there are reactions, everywhere you can basically invoke these ideas, and you can apply these ideas, and you can get your results. Okay, thanks.